The fascinating science and history of Brownian motion. Chapter 1. A microscopic dance. Imagine a single grain of pollen suspended in water. Look closer. No, closer than that. The pollen grain dances like it's at a microscopic disco. This isn't magic. It's Brownian motion. Sorry, no wands involved. In 1827, botanist Robert Brown first observed this jittery dance while studying pollen grains under a microscope. He probably thought, what on earth is going on here? He saw tiny particles within the pollen, moving in erratic, unpredictable ways, like they had too much coffee. However, he observed the same strange motion in inanimate particles of dust and soot. Even dust likes to boogie. The cause of this perpetual dance remained a mystery for decades. Scientists were scratching their heads, and probably their beards too. The key to understanding Brownian motion was to look beyond the visible into the world of atoms and molecules. Spoiler alert, it's a tiny, chaotic party in there. Chapter 2. A collision of ideas. In 1905, a young Albert Einstein published a groundbreaking paper that would change our understanding of the microscopic world. And no, it wasn't about his hair. Einstein proposed that the random jiggling of particles in Brownian motion was caused by invisible molecules of the surrounding fluid. Talk about a microscopic dance party. At the time, the existence of atoms and molecules was still debated among scientists. Imagine arguing over something you can't even see. He argued that the random motion of the particles was due to the kinetic energy of water molecules. Basically, molecules were having a high-energy workout session. These molecules, too small to be seen, were constantly colliding with larger particles. Think of it as molecular bumper cars. The more energetic the molecules, the more vigorous the dance of the particles. It's like a molecular rave. Einstein's paper provided a mathematical framework for understanding Brownian motion, because even particles need some structure in their lives. This was a major breakthrough, allowing indirect study of atoms and molecules, and proving that sometimes the smallest things can make the biggest impact. Chapter 3. From Theory to Reality. Einstein's theory was elegant and compelling, but it needed experimental verification. Because, even geniuses need a fact-checker. Enter Jean Perrin, a French physicist who took up the challenge of proving Einstein's ideas. Think of him as the Sherlock Holmes of particle motion. Perrin realized that if Einstein was right, then the motion of the particles should follow predictable patterns, like a cosmic dance, but with less rhythm. Using a powerful microscope, Perrin meticulously tracked the movements of tiny particles suspended in a liquid. Imagine playing hide-and-seek with particles that never stay still. He painstakingly recorded their positions at regular intervals, carefully controlling the temperature and other experimental conditions. Talk about having a lot of patience. After years of meticulous work, Perrin's results confirmed Einstein's predictions with remarkable accuracy, proving once again that good things come to those who wait and measure. He showed that the particles did indeed move in accordance with Einstein's equations, providing the first definitive experimental proof of the existence of atoms and molecules. Take that, skeptics! Perrin's groundbreaking work earned him the Nobel Prize in Physics in 1926, a testament to the significance of his contributions, and proving that sometimes persistence really does pay off. Chapter 4. Brownian motion in action. Brownian motion is like the secret sauce in both nature and technology. In biology, it's the Uber for nutrients within cells. Proteins and molecules are always on the move, like they've had too much coffee. This keeps essential processes like metabolism running smoothly. No coffee breaks allowed. In the atmosphere, it's like a dance party for pollutants. And it's crucial for air pollution control strategies, because nobody likes a smoggy dance floor. In finance, it models stock price fluctuations, making Wall Street a bit like a roller coaster. Just like pollen in water, stock prices are unpredictable, keeping traders on their toes. Chapter 5. From Physics to Finance. Its humble beginnings as a puzzling dance of pollen grains, which probably left scientists scratching their heads and wondering if the pollen was just showing off. Brownian motion has become a cornerstone of modern science and engineering. Who knew that tiny particles could have such a big impact? Its applications are incredibly diverse, kind of like a Swiss Army knife for scientists. In physics, Brownian motion is used to study the properties of materials and to develop new technologies such as nanoscale devices. It's like the ultimate science hack. In chemistry, it is essential for understanding chemical reactions and designing new materials. Think of it as the secret ingredient in the chemist's recipe book. In engineering, Brownian motion is used to model and optimize a wide range of systems, from traffic flow to the performance of computer chips. It's like having a GPS for particles. The story of Brownian motion is a testament to the power of scientific curiosity, and a reminder that sometimes even scientists need a good mystery to solve. It reminds us that the most profound discoveries can sometimes arise from the most unexpected places, like finding a $20 bill in an old coat pocket, and that the pursuit of knowledge, however small or strange it may seem, can lead to truly groundbreaking insights. So, keep asking those weird questions. Chapter 6. Brownian motion beyond science. But the story of Brownian motion doesn't end with physics, chemistry, or engineering. Its influence stretches far beyond the realms of pure science, touching various aspects of our daily lives in ways we might not even realize. From the financial markets, where it helps model stock prices and manage risk, to environmental science, where it aids in tracking the dispersion of pollutants, Brownian motion is everywhere. In medicine, it's helping researchers understand the movement of bacteria and the delivery mechanisms of new drugs. Picture it as the unsung hero behind groundbreaking medical advancements, quietly working in the background to improve our health. Even in the art world, the seemingly random, yet beautifully intricate paths of particles have inspired patterns and techniques in modern art. It's fascinating to think how an observation of tiny particles can spark creativity across such diverse fields. The ripple effect of Brownian motion is a reminder that the pursuit of knowledge has no boundaries. It teaches us that the impact of scientific inquiry can transcend its original scope, influencing and enriching our understanding of the world in unexpected ways. So, as we continue to explore and question the mysteries of our universe, let's remember to appreciate the seemingly small phenomena that can lead to big changes. And who knows, the next big discovery might just be a tiny particle away. Please hit the like button, subscribe to our channel, and click the bell icon to get notified about our future content.